So let us discuss about effective mass. So let us define some terms. K is a wave vector which is given by 2 pi upon lambda. Similarly, we can write k equal to 2 pi by lambda. So E into h nu can be written as h upon 2 pi into 2 pi upon lambda. So this h upon 2 pi can be written as reduced Planck's constant, uh, the line on h like this, into k. From de Broglie wavelength, we have h by p is equal to lambda. This h upon lambda can be written as under root 2m k. Let us see how. So h by p is equal to lambda, and for p we know p is mv. And how we can say what is mv? Suppose we are going to multiply with v and m and take its root, and let us say into 2 upon 2. So what it will become? It will become p is equals to m square v square into 2 by 2. Now m square v square into 1 by 2 is your energy. So you can write it as half mv square into 2. So p can be written as under root 2m into kinetic energy. So I have used this relation here. So this is the method one. For some material, semiconducting material, the graph E versus K is given by this curve like this. So using Taylor theorem, we can find the nearest curve to given experimental data. For analyzing, we can write this as Taylor theorem. So in mathematics, we are familiar with Taylor theorem as uh, Px is equal to something like the value of P at 0 plus P dash at 0 into x minus 0 to the power 1 plus P dash the P double derivative at 0 into x minus 0 to the square, and so on, upon also upon 2 factorial here, upon 1 factorial, upon here 0 factorial. So that's why this can be written as EC, and here the variable is K. So total energy will be given by EC plus dE upon dK into K plus 1 by 2 factorial d2E upon dK2 into K square, and so on. So P can be written as like this way. And let us say this momentum H by P from de Broglie wavelength, we are going to use this H by P, H by lambda is equal to P, and we are going to multiply 2 pi upon 2 pi like this. So this de Broglie wavelength becomes in this format K into H reduced Planck's constant H bar equal to P. So this K into H bar is equal to 2 into some moving mass of electron m into k. So we can square and we will get an kinetic energy as k square h square upon 2m. So total energy uh, will be given by kinetic energy plus potential energy. So this energy is kinetic term and this energy E naught is potential term. At k equal to 0, these all energies E naught, EC and E equal. So we are going to equate, first we are going to neglecting terms in the expansion. For here we are going to neglecting these higher order terms. After this dot dot dot, we are going to neglect the higher order term, that for k cube, k to the power 4, etc. Let us consider only some terms. So we can equate equation 1 and 7. So what is equation 1 here? Equation 1 is this one equation, and equation number 7. this one. So we are going to equate these two equations, and this one is your 7. So E naught will be equal to EC and E is equals to E. So that's why we will get H square K square upon 2M is equal to D2E upon DK2 into K square. So this K square cancels out and we get the format as effective mass m star is equal to h square into d2e upon dk2 to the power minus 1. This is effective mass or the mass during the motion or at particular energy level. The mass of electron will be given by this equation. This is your effective mass. It can be derived by some other methods that I will discuss in later.